I'm going to talk about the outer limits of contention resolution on matroids with connections to the secretary problem. What is contention resolution? Informally, it's the algorithmic task of converting a random set which is feasible or approximately feasible ex ante, meaning feasible on average, to one which is feasible ex post, meaning always feasible. This is typically studied for packing style constraints like matroids and matchings and so on. And one restriction here is that the output set must be a feasible subset of the input set. In other words, you can think of a contention resolution algorithm as throwing away some of the elements of the input in order to guarantee feasibility in the output. Now, elements of the input set are either assumed to be given to the algorithm all at once, this is the offline model, or revealed online to the algorithm in some order. In the online settings, the algorithm must decide on the spot whether to include an element in the output set or throw it away. Before defining things more formally, let's look at an illustrative example. Suppose you have n agents who are possibly interested in a service. And suppose that agent I is interested, we say active with probability x sub I. The feasibility constraint here is that we can serve at most k of the agents. And suppose we're guaranteed ex ante feasibility in the input, meaning that the expected number of interested agents or expected number of active agents is at most k. This means that the sum of the xi is at most k. A contention resolution scheme in this setting takes as input the set R of active agents, sometimes bigger than k, sometimes smaller than k, and selects a subset T of R of size at most k. Such a scheme is alpha competitive if the probability that an agent is selected is at least alpha times the probability that the agent is active. Now, when these xi's denote independent probability events, there is a contention resolution scheme with alpha roughly 1 minus 1 over square root of k, and this works offline or online and extends to negative correlation. Now for some context. Contention resolution was first formalized by Chakuri et al. And has since been studied extensively. It's been looked at for various constraints like matroids, matchings, and so on. It's been studied offline and online, but almost exclusively when the elements are active independently, meaning that the input set is drawn from a product distribution. Nevertheless, constant competitive schemes have been derived for these various settings. Now, contention resolution is important because it's emerging as a unifying abstraction and a powerful subroutine for a number of applications. For one, it's the final subroutine in randomized rounding for a number of traditional approximation algorithms. And it's particularly attractive there because it tends to provide guarantees that are largely agnostic to the objective. Second, many stochastic selection problems in both online and adaptive data models reduce to contention resolution. Examples include Bayesian mechanism design, stochastic probing, profit inequalities, and we'll see today secretary problems. Now, this talk is primarily concerned with correlation in contention resolution. Most prior work on contention resolution and on stochastic selection problems more generally assumes independence of the stochastic data. For us, that means that the elements are active independently with given probabilities. The results there typically extend to negative correlation. However, positive correlation tends to arise naturally or for technical reasons in many of those applications. For example, in common value auctions, it's natural to imagine that agents' demands for a good may be positively correlated. So this can arise in our illustrative example from a few slides ago. In kidney exchange, matches may be correlated. For example, if one donor matches with a recipient, this could be a signal that that donor is healthy and therefore is more likely to match with a different recipient. In randomized rounding, intermediate steps in the rounding often introduce sometimes positive correlation. And this actually arises in a stochastic matching application studied by Bansal et al. And Adamczyk et al. And finally, we will see in this talk that positive correlation is at the core of the secretary problem. Unfortunately, not much is possible for worst-case positive correlation. But the good news and a major message of this paper is that positive correlation appears to often be benign. Our goals in this paper are twofold. First, we want to understand the power and limitations of contention resolution in the presence of correlation. And second, we want to understand the relationship between contention resolution and the secretary problem. Our focus is on matroids, although some of our results extend beyond. And our results are primarily information theoretic, so I'm not going to concern myself so much with computation. We have two sets of results. First, we characterize the distributions that permit offline competitive contention resolution. And this has a bunch of immediate implications. One is that contention resolution generalizes the matroid-based covering theorem of Edmonds. We also get some closure properties for the distributions that allow contention resolution. And we also can prove limitations on contention resolution when you have to learn the prior distribution rather than it be given explicitly. We also reduce the Matroid Secretary conjecture to and from what we call universal contention resolution online. What do I mean by universal? I mean that it should be as powerful as offline contention resolution up to a constant. Now, the proofs here hinge on the characterization result in 1. I'll mention, however, that one of our reductions has a caveat, so we don't quite get an equivalence. Now we're going to talk about our results characterizing the power of offline contention resolution. What is a contention resolution scheme? It has 3 sets of inputs. First, you have a set system M with elements E and feasible sets I. Second, you have a distribution D over subsets of the elements. And third, and most importantly, you have a draw R from the distribution D. We call the set R the set of active elements. By the way, throughout this talk, I'm going to use X sub I to denote the marginal probability of an element I being active. The output of a CRS is a subset T of the active elements that is feasible. Now, when studying contention resolution schemes, it's typical to restrict attention to only some of the distributions D of interest. The most common restriction is to look at ex-ante feasible product distributions. Those are distributions where the elements are active independently and the probabilities X are in the polytope associated with the set system. For a given CRS, we say it's alpha competitive if the probability that it selects an element I is at least alpha times the probability that the element I is active. For now, we're going to assume that the set of active elements R is given all at once to the contention resolution scheme. This is the offline model. The question we're going to look at is the following. Given a matroid M and a number alpha, which distributions D permit alpha competitive offline contention resolution? For convenience, we're going to call these distributions alpha uncontentious for the matroid M. From prior work, we have some partial answers to this question. We know that product distributions that are ex-ante feasible are 1 minus 1 over E uncontentious, and this extends to negative correlation. We also know that there are positively correlated distributions, even ones that are ex-ante feasible, where no non-trivial alpha is possible. Think of the rank 1 matroid where all the elements show up at once. Despite this, there are some very interesting distributions that exhibit positive correlation that happens to be benign. And now I'm going to describe a very illustrative example of this phenomenon. So consider a rank 1 matroid on the integers 1 through n. Suppose that the active elements R are equal to the integers 1 through I with probability 1 over 2 to the I plus 1. Now this distribution is ex-ante feasible because x1 is a half, x2 is a quarter, and so on and so forth. It's also easy to see that this distribution exhibits non-trivial positive correlation. In particular, the probability that j is in R is 2 to the minus j, but the probability that j is in R given that I is in R is equal to 2 to the I minus j. Despite this positive correlation, this distribution admits a half-competitive CRS. In particular, the CRS that always chooses the largest integer in R. To see why this CRS is half-competitive, notice that once you condition on I being in R, I happens to be the largest integer in R with probability roughly a half. I'm going to ask you to remember this example because it's going to come up again later when we talk about the Matroid Secretary problem. So here's our characterization result. Given a matroid M and a distribution D with R a draw from D, the following 3 conditions are equivalent. Condition A is that D is alpha uncontentious, or in other words, it admits an alpha competitive offline CRS. Condition B is that for all weight vectors W, the expected weighted rank of R is at least alpha times the expected total weight of R. Condition C is that for all subsets F of the elements, the expected rank of R intersect F is at least alpha times the expected number of elements in R that are also in F. I'm going to note that condition C is a finite inequality characterization of uncontentious distributions. And it's a nice exercise to check that the previous example from the last slide satisfies these inequalities. I'm going to point out that the main novelty of this theorem is asking the question. The proof is actually pretty straightforward. In particular, the equivalence of A and B is implicit in the duality arguments of Chakuri et al., and the equivalence with C follows by some simple algebra. There's a number of immediate implications of this characterization. One of them is that contention resolution is a generalization of the classical notion of matroid covering. The matroid base covering theorem of Edmonds is as follows. If you're given a set R of elements, it can be written as a union of k independent sets if and only if for all subsets S of R, the rank of S is at least 1 over k times the cardinality of S. If you stare at condition C, you'll notice that the matroid base covering theorem is saying that the point distribution on R is 1 over k uncontentious. Here are some more immediate implications of the characterization. We get some closure properties. In particular, uncontentious distributions are closed under mixing and closed under independent subsampling. One nice consequence of this is that the mixture of product distributions that are X anti-feasible is 1 minus 1 over E uncontentious, even though such mixtures may have arbitrary correlation. Another consequence has to do with prior independent contention resolution. Consider designing an offline contention resolution scheme for alpha uncontentious distributions. Now, if the distribution is given, by definition, we have an alpha competitive CRS. If, however, the distribution is unknown but can only be learned with a finite number of samples, then we can show there's nothing non-trivial possible. And the proof of this holds even for uniform matroids and invokes the closure under mixing. Now we're going to talk about the relationship between contention resolution and the secretary problem. Let's recall the definition of an offline contention resolution scheme. Now, instead of assuming that the active elements arrive all at once, we're going to assume that the active elements are first drawn by nature, and then all the elements arrive online in some order, one by one. When an element I arrives, the algorithm learns whether or not the element is active. In other words, whether or not the element is in R. If the element is active, the algorithm must decide on the spot whether or not to accept it. In other words, whether or not to include it in the output set T. There's variants of the online arrival model. In this talk, we're going to focus on uniformly random arrivals. We're going to relate this to the famous Matroid Secretary problem proposed by Babayev et al. Here, a matroid is given up front, and an adversary assigns weights to the elements. These weights are a priori unknown to the algorithm. The elements of the matroid arrive again online in a uniformly random order, and when an element I arrives, the algorithm learns its weight and must decide on the spot whether or not to accept it. The algorithm is constrained by feasibility to accepting an independent set of the matroid. This algorithm will be alpha competitive if the expected weight of accepted elements is at least alpha times the offline optimum. The offline optimum is also known as the weighted rank of the matroid. Here the expectation is over the uniformly random order. The Matroid Secretary conjecture is that there is a constant competitive algorithm for this problem for all matroids. A lot of work has gone into designing competitive algorithms for various classes of matroids, but the general problem remains open. So, at first glance, it might appear surprising that there's a relationship between the secretary problem and contention resolution. And that's because the secretary problem is a fundamentally different kind of problem. these weights W are not stochastic. This is a big difference between the secretary problem and stochastic selection problems like contention resolution. Nevertheless, for technical reasons, some people in the community have speculated a connection. We make this connection formal. In particular, we relate the secretary conjecture to the following question. Is universal online contention resolution possible in the random arrival model? By universal, I mean that the online contention resolution scheme should do well for every distribution for which offline contention resolution is possible. And that should include distributions that exhibit this benign positive correlation we talked about. An equivalent way to state the question is the following. Is online contention resolution in the random arrival model essentially as powerful as offline contention resolution up to a constant? We reduce the Matroid Secretary problem to and from this question. One of our reductions is unequivocal. The other reduction has a caveat in it. So let's now talk about the first direction, which states the following. The Matroid Secretary conjecture implies universal online contention resolution in the random arrival model on Matroids. So in other words, if you have a beta competitive secretary algorithm that gives you a beta times alpha competitive online CRS for all alpha uncontentious distributions. So I like to interpret this theorem as follows. Coming up with a universal online CRS in the random arrival model is necessary as a technical hurdle towards proving the Matroid Secretary conjecture. And the key challenge there is how to resolve contention resolution in the presence of benign positive correlation. In particular, how to resolve it online. So let's prove this theorem. Fix the matroid and the distribution D, which can have positive or negative correlation, and let X be the marginals of D. Plot X in Euclidean space. Let's suppose that D is alpha uncontentious, and let R be a draw from D. We want an online CRS such that its output T has marginals in this shaded region. In particular, we want the probability of selecting element I to be at least beta times alpha times xi. By a simple duality argument, it's sufficient to guarantee that the vector y is above an arbitrary hyperplane tangent at the point beta alpha times x. We're going to let w be the normal vector to this hyperplane. And our goal now is to guarantee that the marginal vector y of the output set is above this hyperplane. So we're going to do this by using the following contention resolution scheme parameterized by this vector w. We're going to run a beta competitive Matroid Secretary algorithm with weights wi times indicator of whether I is in R. In other words, active elements get a weight of wi and inactive elements get a weight of 0. So we can now prove that y is above this hyperplane by with one line. So here's the derivation here. So these equalities are by definition and by the linearity of expectations. The first inequality is because we're using a beta competitive secretary algorithm. In particular, the expected weight of selected elements is at least beta times the offline optimum, which by definition for every R is going to be the weighted rank of R. The second inequality is by the characterization of alpha uncontentious distributions, which and that part B of that characterization said that the expected weighted rank of a set is at least alpha times its expected weight. And now that we can guarantee that y lies above a hyperplane like this, we can use randomization to guarantee that y lies in the shaded region. And that completes the proof. Let's now talk about the second direction, which says the following. The Matroid Secretary conjecture reduces to universal online contention resolution in the random arrival model. This theorem is informal because there's a caveat I'm going to come back to later. Specifically, though, the Matroid Secretary problem reduces to online contention resolution for a specific uncontentious distribution I'm going to tell you about in a minute. I interpret this theorem as follows. Designing a universal online CRS in the random arrival model is likely to resolve the conjecture modulo this caveat. The core challenge here seems to be to resolve contention online for these benign positive correlated distributions. Now, the distribution for which we need to resolve contention is that of improving elements defined originally by Karger. The random set R of improving elements is sampled as follows. Let S include each element of the matroid independently with probability 1/2, and let R be the elements which improve the offline optimum on S. In other words, I is in R if I improves the weighted rank of S. A fact that's pretty easy to see is that improving elements hold half the weight of the offline optimum in expectation. And this is because each element in the optimum is improving with probability 1/2. Now, a question that helps build some intuition is the following. What does the distribution of improving elements look like for a rank 1 matroid on 1 through n? And suppose the weights are W1 through Wn in decreasing order. If you think about it for a minute, you'll see that it's precisely the distribution we talked about before, where R is equal to 1 through I with probability 1/2 to the I plus 1. We already showed that this is half uncontentious, even though it exhibits positive correlation. It turns out that this is not a coincidence. We can show that for every weighted matroid, the distribution of improving elements is half uncontentious. In other words, there's a half competitive offline CRS for improving elements. This is our most technically involved result, and the proof is not super intuitive, so I'm not going to show it here. I'm just going to say that it uses the finite inequalities characterization that we had for uncontentious distributions, and the proof involves some careful conditioning and some probability charging arguments that are reminiscent of martingale analysis. Now that we know that improving elements are uncontentious, we can assume universality of online contention resolution and derive the secretary conjecture. Now, once we assume universality, we get a constant competitive online CRS for improving elements. And then we can use the CRS to describe the following secretary algorithm. First, we're going to observe the first half of the elements that arrive online. We're going to look at their weights, but we're not going to select any of them. This is a familiar step for most secretary algorithms. Second, we're going to run this online CRS on the improving elements as they arrive online. In more detail, for each element in the second half, we're going to check if it improves the weighted rank of the elements in the first half, and if so, we're going to designate it active, and then we're going to feed that element and its activity status to the CRS phi. Now, since the improving elements hold half of the offline optimum, and moreover, the contention resolution scheme selects each of them with constant probability, we would get a constant competitive algorithm for the Matroid secretary problem. And that's it. Now, why wasn't I able to say unambiguously that universal online CRS implies the secretary conjecture? This is the caveat that I'm talking about. The answer is as follows. The traditional definition of a contention resolution scheme requires a full description of the distribution to be given up front. However, the distribution D of improving elements as it is encountered in the secretary problem depends on these unknown weights W. Therefore, the online CRS that's used in the reduction must be able to make do with this partial description once it starts resolving contention. And this partial description is based on the weights seen so far. Nevertheless, I have reason to believe that this caveat is not really important and can be removed, and this is based on some ongoing work. In conclusion, prior work on contention resolution and on stochastic optimization more generally often has focused on independent or negatively correlated data, and this was motivated by strong negative results for arbitrary positive correlation. In this paper, we observed that there's such a thing as benign positive correlation, and we characterize the distributions that have such benign correlation so as to permit offline contention resolution. Moreover, we show that the Matroid secretary problem is closely related to the question of extending offline contention resolution to online random arrivals in the presence of this benign positive correlation. And that's it for the talk. Thank you for listening.